Okay, let's get started. We have an application of Newton's law problem, and this problem is relatively long. It has two parts. Each part is by its own a problem. So let's start. We have a motor and a rope was used to pull some heavy equipment, 328 kilograms equipment, including the container, up a slope. So here it is, that container, and the motor is pulling it. The slope has 18 degrees angle of inclination. It has kinetic coefficient of friction of 0.25. The operator started the motor from rest and exerts 1943 newtons of tension on the cable, on the rope. Ignore the rope's mass. Assume the heavy equipment is slowly accelerating. Okay, so we know it's accelerating up the inclined plane at a constant acceleration. So find the acceleration, find normal force, find friction. So that's part one. And let's take a look at part two. At some point, the motor broke, and the operator rigged up some counterweight. So second diagram right here. So the operator must want the equipment up the inclined plane. So there's this heavy counterweight to try to pull it out, to do the pulling. The friction of the pulley is insignificant, and the heavy equipment accelerated at the same rate as when it was pulled by the motor. So how heavy will the counterweight? Essentially, the friction is mostly just between the heavy equipment and the inclined plane that has a coefficient already given. So now we have this how heavy will the counterweight? So counterweight right here. So let me switch over to black. Okay. So first, let's do part one. We'll draw a free body diagram. So let's try to probably go back here. Let's try to draw this right on the body. So we have gravity pulling down. So Fg or W, depending on your notation, and there's also normal force from the inclined plane pushing the heavy equipment away. So here's normal force. And then the motor exerts a force on the cable. The cable exerts tension, so we can just say effectively the motor exerts the tension T against the heavy equipment, and also the inclined plane pulls back with a kinetic friction Fk. Alright, now we have this angle here, 18 degrees. Alright, so since we have already reviewed how to do problems like this on the inclined plane, because the motion is carried out along the inclined plane, we want our x-axis to point along the inclined plane, preferably in the direction of acceleration. So that direction would be the upward inclined plane direction. So we'll use that as the positive x-axis, and the y-axis will point away from the inclined plane along the direction of the normal force. Okay, so let's put our axes here. I will just put an x-axis here, and I'll put a y-axis. I don't really have that much space above, so I'll put y-axis here. So y is this away from the inclined plane, x is along the inclined plane toward the accelerating direction. So I'll also extend the y downward. It's not very parallel. Okay, this is better. So this force, gravity, is not along our axis, so we need to decompose it, assuming it is the hypotenuse of a right angle triangle. So I'll draw this right angle this way. Mark up a right angle here. This is a right angle, and I'll also be drawing another right angle here. Switch back. Okay, so this downward component of gravity, we can call it Fgy or Wy, and this component that pulls the heavy equipment down the inclined plane, we can call it Fgx, or the Wx, whichever notation your textbook uses for gravity. So now the forces are all along the axis, X-axis, let's review it. We have one upward force tension. We have two downward forces. There's friction. There's also a component of gravity. And then along the y-axis, we have one upward force, normal force, and one downward force, the component gravity along that direction. So now it should be sufficient. We can start writing the equations. Alright, so let's call this part A. This part B, I didn't really put them in the original question. So part A, we have our free body diagram. We'll use the x direction, so net force x equals mass acceleration. The net force in x is tension x, tension in the x direction, minus F gravity x, minus Fk is equal to mass acceleration ma. Okay, tension is a known quantity, was given exerted tension 1943. Right, minus gravity is mg. X component, let's take a look here. The x component here in this right angle triangle, it is opposing this small angle, which is the 18 degrees. Or I can use this other right angle triangle. The dashed line is the same length as that, although my drawing wasn't exact. So that's also an 18 degrees. Alright, so x component is the opposing side, so the opposite of our hypotenuse, which is the total. This is the sine, right? So x component takes the sine of 18 degrees and minus the kinetic friction, according to the definition, is kinetic frictional coefficient times normal force. So depending on how hard you push the surfaces together, you can get proportionally more friction the harder you push. And that depends on the two surfaces in contact. And that is equal to ma. Okay. So since we don't know normal force, we can't really solve it. We can try our best to eliminate some of the factors such as mass here, but I don't think it's the right time to do it yet. So let's just leave it here, and we'll call it equation 1. Let's call it A1, part A, equation 1. And we'll move on to the other axis, net force in y. So the net force in y is away from the inclined plane. There's no motion, right? The motion is entirely along the inclined plane. So that is m times a0, no acceleration. This is the advantage of using the rotated axes, because one axis has no acceleration. So the normal force in the y direction minus gravity's component in the y direction is equal to 0. And normal force now is equal to Fgy. And mg, the y component, since the x component is the sine, y component should be cosine. And if we go back to the right angle triangles, this is the y component. It is adjacent to that angle. So adjacent over hypotenuse, that is cosine. Alright, so now we have this. Maybe you're tempted to plug in the numbers, but since we still have that equation, we can plug that equation in there. So we'll call this A2. We actually take the A2 and we try to plug it into A1. Right, so now we have A1. We swap the left and right side because we're interested in solving this A here. So MA equals the T has a value of 1943 and minus mg sine 18 degrees minus mu k. I only partially plugged in the numbers. Normal force is this whole thing, mg cosine 18 degrees. So let's just keep solving. Well, let's actually do this. Let's divide by or multiply by 1 over m on both sides of the equation. So we get a without the m, and 1943 divided by the total mass is 328. Let's put a comma here. and minus, now it's actually going to be G, right? Just a G, no M. This is G, no M. Then you realize the G is actually a common factor, so you can factor it out without having to plug it in two places. Sine 18 degrees minus mu k is 0.25 cosine 18 degrees. Okay, so this way is more compact than what we could have done just by plugging numbers directly to these variables. This is better. It reduces calculations. So use your calculator. Now you can find out the acceleration, and this overall value is 0.56. I kept 2 digits, meters per second squared. As we get to the final answers, we want to quote the units. Okay, so that is finding the acceleration. So the acceleration is solved, and the normal force, this normal force, we could go back to A2. So A2, this equation right here, we probably could have done it over here. Yeah, let's do it here. 328 times 9.8 times cosine 18 degrees, and then you can use your calculator. I already have the answer, and from your calculator you'll get 3060 newtons. Okay, so with the final answer comes the other unit. And then friction. So you can do friction. Friction is this way. So I'll put it here. Friction Fk is mu k times normal force n. Now that we have n, we can calculate this. 125 times 30, 60, and that's a quarter of that. 30, a quarter of that is 1500, 750, right? Close to 750. Use your calculator to get to 765 newtons of frictional force. Also, down to this point, we have solved all the three unknowns. The acceleration is known, normal force is known, and friction is known. Okay, so now we can transition to part B. Part B is a connected system problem. There are two systems, two things are connected in the system. The heavy equipment and also this counterweight, right? So for each object, we draw a free body diagram. For this, this is not supposed to change because the operator wanted to create the same exact acceleration on the box. That means the tension is going to be the same exact thing. So the diagram over here is not going to change, except that over here is a different way to create that 1943 newtons of force. So I only have to draw a diagram here. So let's draw it. I'll do gravity. That was the question. How much mass, right? So gravity here, I'll draw tension. I intentionally drew tension shorter than gravity, so that allows the this counterweight to accelerate downward with a net force downward, right, compared to upward. So this is pretty much the only thing you need to do. So we'll analyze with B. Okay, so part B. So net force in Y is MA. So we're using the same A, and you have a choice of choosing either Y points directly down or directly upward. And what I like to do is I like to choose Y downward because I know the acceleration is downward. If I choose my axis along the same direction, the acceleration is assumed to be positive. I don't have to handle a negative sign. But if you wish it to be upward, that's fine too. You'll find a negative A. You have to use a negative A. Okay, so back to this equation. Because I chose Y axis down, so I chose this. That means all the downward forces will be positive and the upward forces will be negative. So this MA, this is the mass of the counterweight. The heavy equipment is no longer relevant here. So we have this, and mass mg, gravity minus tension equals ma. Since we have plenty of space, we'll just start a new line. This m g minus a. If we just subtract ma on both sides, and then we add tension to both sides, we get this. So that m is equal to tension over g minus a. And we have all of these quantities. 1943 is the tension, g is 9.8, and acceleration was a small quantity, 0.56. But concerning safety, pulling heavy equipment, this is probably not too bad. It's a small acceleration. So now we can calculate. This is almost 1900 divided by 10. You get a little more than 194. So with a calculator, you'll hopefully get the same answer as I did, 210 kilograms. So basically, the second part did not really require a separate free body diagram, but sometimes you'll see just the second part of a question, such as an object being pulled up an inclined plane by another object falling vertically down. Then you'll have to get two diagrams, so one diagram for each object and one equation like this for each axis. So there's two axes for the heavy equipment. There's only one axis because the horizontal axis of the counterweight has no force at all, so there's no need to analyze an axis that has zero force. But zero net force, that still is useful because these force terms will appear in equations. Thank you.